The first part of the webinar, I'm going to do a little slide presentation, just a little bit of the background and the theory about spectral accuracy, how it's a little bit about how it's calculated. And then after that, we're actually going to go into some applications. So we'll do a real live software demo showing how you can utilize this principle for actually a variety of different mass spec analyses. So again, feel free also to join us tomorrow and Wednesday at 1 o'clock Eastern Standard Time. And on Tuesday, the topic's going to be, that's tomorrow, improving and automating GCMS compound ID on quadrupole MS using accurate mass, spectral accuracy, retention index, and conventional search. Then on Wednesday, the topic's going to be differentiating the loss of 43 Dalton EI fragments, for example, C3H7 or CH3CO with single quad GCMS. And as you may sit down there and calculate, you'll realize those are very closely spaced ions. And even on a quadrupole, we can easily differentiate and even semi-quantitate them. So let's get started. The topic today is mass spectral accuracy. What is it and why is it so important? First off, just a little background. This is a typical ion profile, LCMS for the molecular ion of the compound C25H23N2OS. And if you run your mass spec at a quadrupole, for example, at resolution 800, this is typically what you'll see. You'll see a pattern of sticks, okay, known as centroided data, and this is probably what you're used to working on a day-to-day basis. However, in reality, what the instrument actually does before it presents the data to you is it actually does a full profile mode scan. This is a continuous acquisition over the mass spec. You can see now that the centroid peaks are actually broader bands, and the width of those bands is really an indication of the resolving power of the mass spectrometer. And what happens is once the mass spectrometer scans this data, acquires this profile mode data, which by the way is also sometimes known as raw data or continuum data, it actually does the centroiding process, and we'll get into a little bit more detail about that. And it pretty much picks the peaks for you and just displays it as centroid mode data. And that's pretty much what we're used to as mass spectrometrists. And some of that is historical because the centroid data is obviously much highly compressed data. But unfortunately, when you do that, as we'll see, you're throwing a lot of information away that we can take advantage of. Now, what this is it looks like a centroid data, but actually this is a theoretically calculated mass spec. And we'll get into this, but mass spec is unique. We can calculate based on first principles exactly what a mass spectrum should look like for any given formula. And this is a theoretical mass spectrum at infinite resolution. So the instrument has infinite resolving power. Although if we look at more detail, we'll see if we look at the A+1, you'll see the isobars there, okay, around which primarily is the C13 peak. And at A+2, you can see it's very rich in information. And obviously, if you centroid by just locating that peak, you're going to lose all that information. And that information contributes to our ability to help identify or quantitate that particular compound. And in fact, even at low res, like on a single quad instrument, these are all different ion profiles of compounds that have almost the identical mass. They're within a few parts per million of each other in terms of mass accuracy, but they have different formulas. And because they have different formulas, they have unique isotope patterns. And in fact, if you look at the A+1 peak, you can see that the contributions for that include C13, sulfur 33, N15, deuterium, so on and so forth. And in summary, really the beauty of mass spectrometry, and this is quite unique for mass spectrometry, is every unique formula has a unique mass. And that's one of the things that makes mass spec so powerful, because if we can get an exact mass measurement of a given ion, we can identify its formula uniquely. In reality, we don't have infinite resolutions, but we can still do a pretty good job. The other thing is that sometimes gets ignored or is not emphasized as much, is that every unique formula has a unique ion profile. And that information is highly underutilized. And that's a shame, because we can accurately calculate the mass spectrum of any given formula to a very high degree of accuracy. But unfortunately, we cannot accurately match the ion profile of a measured spectrum. This is where we're going with spectral accuracy. The reason that we can't do it is because we don't know the line shape of the mass spectrometer itself. And as we go along, we'll explain pretty much what that means. So let's talk about conventional mass spectrometry and how the calibration within the instrument works. It's a little more complicated, but the primary thing that is being done when you run a tune is to basically calibrate the mass axis. It's also the line shape too, but we're not going to get into that detail right now. And this is what your instrument, again, measures. This is the profile mode data. This is always the raw underlying data. So it measures that, and that would be a calibration standard such as PFTBA gas and a GCMS, or a tune solution in LCMS. And the software knows that for a given compound, that the mass position should be over here, where indicated by the peak of the blue band there, and not of the black. So what the calibration does essentially is does a x-axis shift or correction to try to get better mass accuracy. And that's pretty much what gets done in a conventional calibration. Now, what we're going to talk about, which is going to lead us into spectral accuracy, is a very different kind of mass spec calibration. What we do is we start out with our ion profile from our measured standard. And in this case, we need to know a little bit more than just the mass of the standard. We actually need to know the formula, because we're going to calibrate not only the mass position, but we're going to calibrate the whole isotope profile. And the first thing we do is we estimate the resolving power of the instrument. So quadrupole, for example, around 800. So we simply pick a line shape that has about the same line width as the measured line width with your instrument. And we take that line shape and we put it aside for a second. And since we know the formula of our standard, again, we can calculate the theoretical infinite resolution mass spec. And again, this is something that's unique to mass spec. But this is not what our instrument measures, because our instrument is always convolving, has a limited resolution, which is approximated by this Gaussian function here. So that Gaussian could be another line shape as well, but let's assume it's Gaussian. Is a mathematically well-defined function. And if we convolve that with our theoretical infinite resolution spectrum, we get a nice looking mass spectrum, which, boy, I wish all mass spectrometer data looked like that. It looks really nice and symmetrical. That's because we know the line shape. We know exactly what it is mathematically. And if you compare that to the measured spectrum, you see it's quite different. It's shifted in X, but it's also shifted in shape, and that's called the line shape. So the line shape of your measured mass spectrum, which is this funny little wiggles here, it's actually quite reproducible and consistent. The problem is I don't know what it is. It's not mathematically defined. So how do we compare theoretical mass spectra with measured mass spectra? Well, we can't do it very well. But what we can do in our calibration here is we can, using a little bit of linear algebra, we can calculate a correction function, which kind of looks like that. And what it will do is that when it is applied to the measured mass spectrum, it will basically correct the mass spec not only in the X or the mass position, but also it'll correct the line shape as well. So it'll have a nice, well-defined Gaussian line shape. And once we've calculated that correction function, we can simply measure the unknown spectrum of whatever compound you're measuring. It doesn't have to be the same, it could be a completely different compound, has no relationship to the calibration standard, and we simply apply it. And what we get is we get a calibrated mass spec. The difference between this mass spec that's calibrated is it's calibrated not only in X, but it's also calibrated to a known line shape. And this is very important. And that's just a comparison to the uncalibrated data. So X and Y have gotten calibrated. So what does that give us? What advantages does that give us? Well, the first thing it can do is it can give us significantly better mass accuracy, even on a unit resolution, i.e. quadrupole type instrument, and up to 100 times quite easily. How is that? Well, if you look at the bottom here, this uncalibrated line shape, how do I find the peak position, this exact mass position? Well, I don't know what the line shape is here, so all I can do is maybe look for the maximum, or maybe I look for a few points around the maximum, and I say, oh, that's got to be the X position. And fortunately, the line shape changes across the mass spectrum, and so it'll shift around if you don't do a full calibration, and it gets really complicated, and you don't get great mass accuracy. And you should be aware that mass accuracy is different from resolution, and we'll talk a little bit about that. So typical vendors will maybe specify about 0.3 Daltons as the mass accuracy of a quadrupole. Now, if we calibrate the line shape, okay, using the methodology that I just discussed, since we know what that line shape is, in this case, we're showing that it's a nice Gaussian, when I do peak picking, I can fit the entire Gaussian function across all the data points on that particular peak there. That's much more accurate than a single peak, because you're taking advantage of the noise and the shape and so on and so forth. So that now gives us the ability to get mass accuracy on a quadrupole down to the third decimal place. So down to about the third decimal place there. That's about 100 times better than we get on a normal uncalibrated quadrupole mass spectrometer. Now, the other thing that it gives us is it gives us what the subject of this talk is, which is spectral accuracy. And we can get spectral accuracy easily within the 99% range, plus or minus. And let's take a look at that. What are we doing with spectral accuracy? What we're doing is we're matching the isotope profile of a calculated mass spectrum. Remember, we can calculate mass spec exactly. That's that kind of yellowish green line there. That's the calculated mass spec of that particular formula. And this is the measured. And of course, since we don't know the line shape, we can't really match them up that well. And you can see there's a lot of gaps here. There's a lot of overlap. And if we do our calculation of spectral accuracy, and again, so the spectral accuracy is the goodness of match between a calibrated or between a profile mode mass spectrum and a theoretically calculated. And without the ability to do line shape calibration, that's very difficult to do. In this case, we get about an 89.9, 90% spectral accuracy. That's actually pretty poor, as we'll see when we get to a little bit of our demo. And you can see there's like huge mismatches here between the two spectra. But once I've calibrated the line shape, I can now not only get accurate mass, but I can also compare these isotope profiles very accurately. That's another metric to help us do formula identification, as well as a number of other things that we're going to talk about. And you can see the overlay now of the two lines, and they're almost exactly on top of each other. And in this case, we have about a 99% spectral accuracy. So that's another way to identify an unknown ion, is using spectral accuracy. But you can't do it unless you calibrate that line shape. Very, very important. So that is a brief introduction to spectral accuracy. I told you I was going to try to keep this short. But what we're going to do is I'm just going to jump into the software. I'm going to show you a couple of examples of what we can do with this calibrated data. and hopefully it will become clear. And again, we'll do questions and answers at the end. Okay, so let's go to our software. This is our software. It's called MassWorks. And let me just close all the data windows here. And I'm going to open up, this is it. First thing I'm going to open up is a GCMS run of a VOCs. And it's basically, you see this little dialogue that popped up. What it's saying to me is it says, oh, by the way, remember, you have to go through this calibration process. It's saying to me, oh, by the way, you already did the calibration, so I'm just going to apply it. And in fact, for GCMS, there's a built-in calibration standard, PFTBA gas, and you can actually turn it on during your method, and the software will automatically recognize it and automatically calibrate your data to accurate mass and as well as the line shape, so you can attain high spectral accuracy. So let's take a look here. We'll zoom in on one of the bands here. This is the molecular ion here. I'm going to zoom in. This is EI fragmentation. You see the isotope pattern. I say, oh, well, first thing is, you know something about mass spec. So you know there's got to be like probably chlorine or bromine in this particular sample. And since it's VOCs and, you know, there's a lot of chlorinated and brominated compounds of interest, indeed, that's certainly possible. Notice that the peaks are labeled to 4 significant digits. 3 of them are actually significant. As we talked about, we get about 100 times better mass accuracy. Now, in a high resolution instrument, what you would normally do if you want to identify the formula, if we didn't know what this was, is we could go into the software, and in our software, we call this clip search. We'll talk a little bit about why we call it clips. And typically what you'll do is, you know, kind of the accurate mass capabilities of your instrument. Now, this calibration isn't going to beat out a TOF instrument in terms of mass accuracy, but it's going to start to get us close to our ability to determine unknown formula IDs. And then what you do is, you know, the typical elements that are in this particular compound for this molecular weight. And what we'll do is we'll do a search and we'll find all formulas that meet that criteria, and we'll list them within a 30 milladalton window of that particular peak. So what we get is about 31 compounds. So you have to decide now which is the correct answer. And even in a high resolution instrument, you're going to get not a single match, you're going to get multiple matches. So having other ways to determine a compound identification besides mass accuracy is actually pretty important. Now, if we click here on our list, let's say down here, and says, you'll see this is the compound I'm looking at. And what it's doing is it's overlaying the theoretical mass spectrum, okay, which is in black there, and along with the over the top of the calibrated. And we go down here, you see 77% spectral accuracy. You can see the mismatches. It's pretty horrible. It's obviously, that's not the right isotope pattern. Even if it was uncalibrated, you probably could tell the difference there. But as we get up closer to the top here we have something that's about 96%. Okay, it's got a pretty good match. There's some things lacking down here. On an uncalibrated data, you'd start to run into real big problems of struggling. In fact, you'd probably run into struggles, like we said, at about 90 or 80% spectral accuracy. And if we go to the top here, and we're overlaying this compound with calibrated mass spec, so the theoretical over the calibrated, and it matches really, really well, over 99% spectral accuracy. So we think that the formula there is C6H5Br. So we haven't done any library searching, matching, whatever. This is a total unknown unknown. Now I can verify this. I can, if it is in the libraries that we can actually do EI search, I could do a library search. And if it's in the library, we got a nice match here. It decided that the compound is probably C6H5Br, C6H5Br. Lo and behold, we get the right compound. So this is a very powerful concept for application on the quadrupole to do things that normally would be way out of their range of capabilities. Okay, and really quickly, I'm going to skip to this particular peak here, which is kind of interesting. This is the molecular ion. We can see it here. This is the peak of the molecular ion. Again, you get all the decimal places there. But you notice something interesting here. You'll notice that before the monoisotopic peak here, there's a couple of other peaks. So what are they? So most likely in EI fragmentation, what happens is not only do you get a given ion, but a lot of times you'll also strip off an additional proton. So you'll get M minus H, or in this case, even M minus 2H. The problem is those lines are overlapping with the molecular ion. So the molecular ion minus H and molecular ion minus 2H are overlapping. So how the heck are we going to identify this with spectral accuracy? Because if we do the search, what you'll see when I do the search, and I'll just leave all those compounds in there, we're going to get a pretty lousy spectral accuracy. And you can see it's not working out too well. Not bad, but it's not great. And the reason for that is because of the interference of these other peaks. But since we know what the underlying spectra of those other components look like, we can just simply take them in account and do a little linear algebra. So now what I tell the software is we're going to also look for minus H, minus a proton. In fact, we're going to look at 1 or 2 as options. So it's going to try to find the amount of the molecular ion minus H, and the molecular minus 2H. Now I do the search, and lo and behold, the spectral accuracy is 99.6%, almost perfect match. And you can see the overlay here. So the point is that once we know what the line shape is, and since we can calculate mass spectra, we can easily look at mixtures and do all kinds of very interesting stuff that isn't even possible on high resolution instrument. For example, let's look at this particular example here. This is interesting. This is actually a labeled compound. It's a drug. It's HCT is its common name. It's hydrochlorothiazide, and it's labeled with deuterium at one point, at one place on a ring, where 2 hydrogens can get replaced by 2 deuterium. So if I zoom in on the molecular ion peak there, what you'll see is funny looking bands. This is actually the monoisotopic peak, but you'll see the second peak is bigger. That's because it's a labeled compound, not surprising. So how do we deal with this? They're all overlapping. Even in a high resolution instrument, if we wanted to try to quantify the amount of deuterated and non-deuterated compound, it's very challenging. But what we can do when we do our search match here is I can say, okay, in my little ion series here, I say, consider, in addition to the normal compound CHN, and I fixed all of these values because I know exactly what the compound is. It's C7, H7, N3, O4, S2, CO1. It's not an unknown identification. I want to semi-quantitate the labeling, the labeled and the unlabeled form. So what I tell the software is like, okay, take away 2 deuterium or take away 2 hydrogens and add 2 deuteriums, and then consider that spectrum. So you do the search. Again, I only get one match because I specified this formula specifically. You'll see the overlay is really nice. So what it's doing is it's finding the best fit of both the deuterated and the non-deuterated form to this isotope profile. And again, this is only possible because we can calibrate and we know what that line shape is. And if I put my little mouse over here, the formula, you might not be able to see it, but that actually gives me the relative amounts of the 2 species. So what it's telling me is it's 30% non-deuterated and 70% deuterated. That's a very difficult problem to do any other way. So the next question I'll try to answer is, what can this do for us for high resolution instruments? Well, high resolution instruments have nice sharp bands. The mass accuracy is quite good. We really can't do a lot to improve that mass accuracy, but we can still help you out with the spectral accuracy. So this is just the TOF instrument. It's a simple infusion run. I'm going to look at the particular compound here at 241. You'll see nicely resolved band. Okay, and let's try to do our search here to identify that unknown. And you'll notice that this CLIPS, which is the normal search that I do that uses the calibrated line shape, is grayed out. That's because I haven't run a calibration sample. But lo and behold, this is high res. And the monoisotopic peak here, the first peak, is by definition isotopically pure. Okay, so that means it's a perfect line shape representation. And I can use that as the calibration line shape and not even bother with an external calibration run. So that's pretty cool. So we call that self-calibration. So I run that type of search, and it's high resolution. So I'm going to constrain the mass accuracy to 5 ppm. It's a really good run, well-calibrated instrument. These are all the elements I'm going to consider, and I do a search. So the point is that even at 5 ppm, high resolution, using chemical constraints, I still get 39 compounds to evaluate. Now, a lot of these you can look at them and you can throw them out. You might know something about your sample, but I sort them here on spectral accuracy. And if you look here, you'll see if I zoom in. Let me clear it up a little bit. I'm just gonna hide the raw. So that's an overlay, okay, of the of this particular formula, which has a spectral accuracy of 90%, and obviously the isotope pattern doesn't match very well. If I go to the top match, what you'll see is an almost perfect match at 98.2% or thereabouts spectral accuracy. Typically, high resolution instruments, believe it or not, are not quite as good in terms of linearity. You may well know this. So you'll get somewhat less spectral accuracy, but still good enough spectral accuracy to basically do very good formula identification. And even the second compound here is significantly different in the match. So that's a unique match. You don't always get that. Typically it'll limit from these 40 compounds that are on the search list. You'll probably get 3 that are pretty close matches in terms of spectral accuracy, but that's a huge bonus in terms of helping do unknown formula ID. So that's it. I'm gonna turn off my display here, and then we'll take any questions that you might have. Yangdong, you want to answer this?
Sure. So the question was there's the customer has a single quadruple LCMS Waters QDA and thermal LTQ. The mass accuracy is plus minus 0.1. Using MassWorks, would it improve the accuracy to 0.0001? Okay. So on the quadruple system, the Waters QDA, for example, the single quadruple system, if you do calibration right before the run, which would address any drifting problem on this low-cost single quad system, the mass accuracy can be improved by a factor of 100 typically. So it'll go down to a few milli-Dalton. Okay. So that's on the quadruple system. On the thermals LTQ, which is not exactly ion trap, but it's a linear trap. So it's in between ion trap and a traditional quadruple. So it suffers from the typical errors related to the fundamental physics of the ion optics. So the mass accuracy improvement would not be a factor of 100. It'll be most likely a factor of 10 or 20. So it'll go down to the second decimal point on the LTQ. Similarly to SciX a linear trap, Q trap, for example, the mass accuracy would not be as good as a traditional quadruple system, but it will be a significant improvement of 10 to 20 times.
You want to take that one, Youngdong?
Okay, well, I would alter that. It's a question from Professor Dan Kirshner. I assume everybody can see the question, right? So I don't have to repeat it.
Yeah, you have to repeat it, I think.
Oh, okay. So the question is that when you first got those small peaks to the left of a large monoisotope peak, you broadened your elemental composition by allowing for -H and -2H. Why did the fit curve in black not fit the presumed -2 peak, whereas the -1 peak was fit well? That was simply due to a parameter setting. So if you see only one small peak to the left of the monoisotope peak, that's typically an indication there's a -H version. And if you see another additional peak to the left of the large monoisotope peak, that typically means there's a -H. There's also a possibility of -2H.
Yeah.
The software would allow you to do that, except that you have to also start the spectral accuracy mass window a little further to the left to -2 or -2.5 to include that -2H peak into consideration, which will allow the fitting curve to cover the
that's actually shown right here. I think is what he's talking about. So we only told the fit to happen starting at about 1 Dalton from the monoisotopic peak, but I can change that. So I can go and do the search. And for example, I want to start at about -3 or -3.5 from the monoisotopic peak. And now when I do my search and I look at the overlay, you'll see that it's also now fitting those other components. It's just a matter of the range of the fit. Okay, so just a reminder, tomorrow we're going to talk about an application of an automated system for GCMS specifically, which will apply some of these technologies automatically to an entire GC run, and also includes retention index capability, which is automated and uses commercial libraries to improve your confidence of your unknown ID. And then on Wednesday, actually, Yongdong will be presenting, which is an interesting case similar to what we're talking about here, except we have very closely resolved bands, and even on a low resolution instrument, we can identify the correct compound type by using this concept of spectral accuracy and line shape calibration. So I think that's probably about it for now. I want to thank everybody for attending, and hope to see you.
Hold on, there may be another question.
Okay.
Let's zoom the chat box. So the question is, hypothetically, if my standard has many small intensity peaks and 2 high intensity peaks, how well can MathWorks identify the correct isomer of, say, 3 very similar isomers? I can take a first crack. Don, you can chip in. So if you have what's purportedly a standard typically considered pure standards, or 98% or 95% standard that you purchase from Sigma Aldrich, for example, and you run them through your either LC or GC system. If you have chromatographic separation and there are two additional isomers blending into the standards, those three total compounds may be chromatographically separated or maybe not. If they are chromatographically separated, it's no longer a problem because you can identify each and every one of them individually by limiting yourself to a specific retention window. All right. So whether you have absolutely pure standard or not, it's of little or no concern in that case, because even though you have isomer impurity, they are chromatographically separated. Now, if you don't have chromatographic separation and the isomers are by definition having exactly the same elemental composition, their molecular ion in the case of EI spectrum would be identical. So mass spectroscopy. So from mass spectrometry perspective, you cannot differentiate them. They'll come up as a single compound with the same elemental composition. You might not even notice you have additional isomers co-mixed in if they're not chromatographically separated. Now, if the isomers have different EI fragmentation patterns, or even different unique fragmentation ions, you can spot them by examining the EI fragments and identify the presence of possible isomers and impurities. I hope that answers the question to some degree. Sure. Any other questions? Feel free to email us at info@cernobioscience.com. We'll be happy to engage you in further conversation.